All right, today we're going to look at reviewing for our Chapter 6b test. Our first topic is to simplify each expression. Assume all variables are positive. That means we're not going to worry about needing absolute value bars. Our strategy is to simplify the fraction inside our parentheses first. So when we look at this first example, you'll notice that there are some x's both in the numerator and in the denominator. We can clean that up. There are no common factors for the 8 and 27, so we're going to leave that for a minute. But our x's, we have 7 on the top in the numerator and 1 in the denominator. We have 6 extras in the numerator. For the y's, we have 8 in the numerator and 5 in the denominator, which means we have 3 extras in the numerator. And then remember, a 1/3 power means we're doing a cube root. So we could change this instead of a 1/3 power to just say we're taking the cube root. They're equivalent. We've done this type in the first half of Chapter 6. The cube root of 8 would give us 2. The cube root of 27 is 3. We have x to the 6th. We're using groups of 3, which makes 2 full groups. And for our y's, we have 3 of them being multiplied. When we cube root it, we get a single y. Okay, for our second one, because this has a negative exponent, we can think of moving it up. Then we can add those exponents together, so we have x to the 4th. And then when we have a power to another power, we multiply those powers. So if we take 4 times 3 halves, we get 12 halves or 6. This becomes x to the 6th. Okay, our next set, our strategy is to deal with the negative exponent by moving it down first. Anytime we have a negative exponent, we're going to flip it. So for this one, our negative 125 is to a negative 2/3 power. Because this is negative, let's go ahead and flip this over. So now our negative 125 is in the denominator, but it's to a 2/3 power. Okay, so remember, when we have a fraction power, the top number is our power, and the bottom number is our root. So this says we're taking the cube root of negative 125, and then we're going to turn around and square it. Well, the cube root of negative 125 is negative 5. When we square that, we get 25. So our answer is 1/25. All right, for this one, we do have a negative exponent here, so let's think of moving that down. We have 16x to the 8th. We're dividing now by y to the 10th. And since the whole thing is to a negative 1/2 power, we can flip that whole fraction. So we're going to get y to the 10th over 16x to the 8th. And now it's to a positive 1/2 power, which is just a square root. Y to the 10th to the 1/2 power, half of 10 is 5, so we get y to the 5th. For the denominator, 16 to the 1/2 power means we're square rooting 16, which gets us a 4. And then x to the 8th to the 1/2 is x to the 4th. 4 full groups when we have the square root of x to the 8th. So we have y to the 5th over 4x to the 4th. All right, next one. We're simplifying each expression. Again, we're assuming all variables are positive. This one we have the common base. They're both t's, but they're different types of roots. This is a square root of t times a cube root of t. So when we look at it with these radical notation, we can't do anything. But if we convert it to these rational exponents, then we can. We use our addition and subtraction rules of exponents, just like we would if they were whole numbers. So let's get a common denominator so we can add these fractions together. So 1/2 I'm going to think of as 3/6, and 1/3 we think of as 2/6. So I'm timesing that one by 2, I'm timesing this one by 3. We now have a common denominator of 6. We can add those exponents together, and we get t to the 5/6. I would accept that answer. We can also convert it back into its radical format if we want. It's the 6th root of t to the 5th power. But since our original question was given with fraction exponents, we can go ahead and leave it like that. Our next one, we have a radical notation, but again, remember the index here is different, but we do have a common base. They're both 5s. So if we write this as 5 to the half power instead of a square root, and 5 to the 1/4 power instead of a fourth root, now, because we have a common base, we can combine those exponents. We have some on top, some on the bottom. We need a common denominator, so the 1/2 I'm going to times by 2. So we have 5 to the 2/4 divided by 5 to the 1/4. And now we can just subtract our powers. 2/4 minus 1/4 leaves us with 1/4. So 5 to the 1/4, which would be written as the fourth root of 5. Again, we're putting it back into that same type of notation that we had initially. All right, our next set of questions, we are looking at solving. We do need to remember to check for extraneous solutions. So our strategy here is to raise each side to the power of our index. So if we have an index of 2 here, a square root, that means to undo it, we have to square it. Whatever we do to one side, we have to do to the other. And remember, on something like this, we're going to have to picture foiling that out, because x plus 4 squared means we're multiplying by itself. So on the right-hand side here, we end up with x squared. Outsides, we get 4x, and insides, we get 4x, so a total of 8x. And our last term, 4 times 4, would be 16. On the left side, our square is going to cancel our square root, and we just get x plus 6. And because we have an x squared, we have a quadratic equation that we're solving. We need to get everything to one side, so we have one side equal to 0. So I'm going to subtract the x and the 6 over to the right. That leaves me x squared plus 7x plus 10. And then we can solve that quadratic by factoring. We need two numbers that multiply to be 10 but add up to 7. We can use 2 and 5. And then we look for solutions to this. So x plus 2 could be the 0 when x is negative 2. And x plus 5 could be my 0 if x is negative 5. Now we do have to check these. And remember, we always go back and check in our original equation, which was the square root of something plus 6 equaling something plus 4. Okay, I'm going to write that out twice because I do have two of them to check. All right, so let's check the negative 2. And here we'll check our negative 5. All right, for our first one, negative 2 plus 6 is 4. The square root of 4 would be 2. On the right-hand side, negative 2 plus 4 is 2. Since they are equal, it means that is a solution. It's working. On the bottom one, negative 5 plus 6 is 1. The square root of 1 is just 1. On the right side, though, we have negative 5 plus 4, which is negative 1. Those are not equal. That means this is extraneous and would not be included as one of my final answers. All right. Our next one here, to undo a cube root, we would have to cube both sides. On the left, the cube and cube root cancel each other out. We get 5x plus 2. On the right-hand side, 3 to the 3rd power is 27. This is just a linear equation, so we can go ahead and solve it like we've been doing. 5x would then equal 25 once we subtract 2 to the other side. And then dividing out our 5 dividing by 5 gives us x equaling 5. Okay, let's check that. We have the cube root of 5 times something plus 2, and it's supposed to equal 3. Okay, we're going to plug a 5 in. 5 times 5 is 25. Add the 2, we get 27. The cube root of 27 does equal 3, so it is a solution. All right, moving on. Our next topic, we're solving again, checking for extraneous solutions. This time we're going to use reciprocal exponents to cancel things out. Our instead of having a fourth root symbol, we have this 1/4 power. But remember, the bottom number is our root. So we are taking a fourth root. To undo that, we're raising it to the 4th power. So the reciprocal again of 1/4 would be 4/1. Okay. Raising to the 4th power on the left side leaves us with just 3x plus 1. On the right side, 2 to the 4th would be 16. Again, we just have a linear equation, so we're going to subtract our 1 over. Try to get x by itself. Divide out our 3. And we end up with x equaling 5. All right, plugging that back in to check. We have 3 times 5 plus 1 to the 1/4 power is supposed to give us a 2. 3 times 5 is 15, plus 1 is 16. 16 to the 1/4 power does equal 2. So it is the correct solution. All right, on our next one, we have to first get rid of this 2 because we're trying to isolate the piece that's inside either the root symbol or raised to that fraction exponent. So we want this part here to be all by itself. So let's divide out our 2. We get 3x minus 3 to a 2/3 power now equals 9. To undo a 2/3 power, we have to use the reciprocal, which is a 3/2. But remember that we are now doing an even root, and this is where we need that plus minus. So we want plus minus the square root of 9. We then have to cube that to take care of the 3 on top, that power. The left side cleans up. The 2/3 power and the 3/2 power cancel each other out. So we get 3x minus 3. On the right side, square root of 9 is 3, so we get plus minus 3. When we cube that, we end up with plus minus 27. Okay, now we have 2 separate values, so we really have 2 equations. Let's split this up. 3x minus 3 could be negative 27, or 3x minus 3 could be positive 27. For the left version, adding 3 over leaves me negative 24. Dividing by 3, we get negative 8. On the right side here, adding a 3 gets me 30. Dividing, we end up with 10. So we have an 8 and a 10. We need to go back and check those. Let me give myself a little more room here. All right. So checking the negative 8. Again, we have to go back to the original problem. So 2 times the quantity 3 times negative 8 minus 3 to the 2/3 is supposed to be 18. 3 times negative 8 is negative 24, minus 3 more is negative 27. To a 2/3 power, if we take the cube root, we get negative 3, then we square it, we get 9, and 2 times 9 does give us 18. So that one did work. Checking our 10, we have 2 times the quantity 3 times 10 minus 3 to the 2/3. We're supposed to get 18 again. 3 times 10 is 30, minus 3 is 27. We have to raise it to a 2/3 power. So we cube root 27 and we get 3. And 3 squared is 9, and 2 times 9 gets us 18. So both of those solutions did work. All right, moving to our next section. We are given 2 functions. The first one, f of x equals x squared minus 6, and g of x equals x plus 2. It says to perform each function operation and then find the domain. Strategy. For polynomials, they have a domain of all real numbers. Then exclude anything that can't be used. Watch for square roots, because we can't have negative values under our square root. And watch for denominators, because we can't have a 0 for a denominator. All right, so initially we have x squared minus 6, basic polynomial. Domain for function f is all real numbers. Same with g, basic linear polynomial. So domain for g is also all reals. So we don't have any restrictions right now. When we go to do our division problem, though, we have created a fraction. And so this denominator that we have as g of x, which is x plus 2, and f of x, which was x squared minus 6, we have to worry about that denominator being 0. So we want to make sure x plus 2 never equals 0. That means x, if we subtract 2 over, can never equal a negative 2. So my solution to the question here, the operation I was doing a division, I end up with x squared minus 6 divided by x plus 2. There's no way to factor x squared minus 6 and get anything to reduce out. So that's my final answer. My domain for my answer, though, x can't be negative 2. So we'll say domain, all reals, except negative 2. For the next one, they're just asking me to do a subtraction of the two functions. We do have to be a little careful here because we're taking function f, x squared minus 6, and we're subtracting function g, x plus 2. And we have to remember then to distribute that negative to that whole g of x function. So we have x squared minus 6 minus an x minus a 2. And then let's just put that in standard form. Highest power first would be x squared, then our minus x, and then we can combine our like terms here to get us a negative 8. So my answer would be x squared minus x minus 8. Again, that's a basic polynomial, so my domain would just be all reals. And again, we can use that capital R to represent that. All right, moving to compositions. It says to find the composition of the functions, strategy to rewrite so that we can see that you're putting a function into another function. We really have to watch our order here. So remember that when we see this notation, it's really equivalent to this. It's saying we're putting x into f, and then we're putting that answer into g. Okay? So we're taking basically a function f of x, and we're dumping it into function g. So function f is going to go into function g. Okay, so we start out writing function g and just leave a hole where the x was. So now I can dump in function f, 3x minus 5. Notice on this one we do have to square our 3x minus 5. So let's think of foiling that out. We end up with 9x squared. Outsides and insides are both negative 15x, which gets us negative 30x. Our last term, negative 5 times negative 5 is 25, but we also have this negative 2 here, so we're actually going to end up with 27. Okay, so that is my composition. Now, right below it, it says find g of f of negative 2. We have two ways we can do this. We can plug negative 2 into function f, and then take that answer and plug that into function g. But we've already done this composition, so we know what the composition should get us. We can simply put a negative 2 into this. So 9 times negative 2 squared minus 30 times negative 2 plus 27. Negative 2 squared would be 4 times 9 is 36. Negative 30 times negative 2 would be a positive 60. And if we add that all up, we get, what, 96 plus another 27 would be 120. Hang on. What did we say? 96 and 27? 123 would be my answer. Okay, for the next one, we have function f is 4x plus 7. Function g is x plus 2. we are finding this time f of g. That means we're putting g of x into function f. Okay, g of x is going into function f. So we're going to start with function f, and in place of our x, we're going to substitute in g of x. Okay, simplifying now, distributing our 4, we get 4x plus 8, plus that other 7 on the end. We end up with 4x plus 15. All right, our next topic says find the inverse of each function and then determine is the inverse a function itself. So our strategy, to find the inverse, we switch the x and our y values, then we solve for our new y. To determine if it's a function, we decide on the shape of the original function and then determine what the inverse will look like. And remember that vertical line test. So our first function f of x is 2x squared plus 6. If we visualize what this looks like, because it's an x squared graph, it's a parabola. Okay? We're going to find the inverse. Remember, f of x is really like our y, so we switch our x and y. So x equals 2y squared plus 6. To solve for y now, we have to subtract our 6 over. We then would have to divide by 2. And then we'd have to square root. And remember, whenever we square root, we get that plus minus. So we end up with y equaling plus minus the square root x minus 6 divided by 2. Okay, so that is my inverse. Y equals plus minus the square root of x minus 6 divided by 2. Is it a function? It is not, because remember our square root graphs are those sideways. Parent function for square root of x is this, and the bottom half would be our negative square root of x, the reflection. So when we have that plus minus, it means we're getting two separate little square root graphs connected, and that would not pass a vertical line test. So is it a function? Is the inverse a function? No. And our reason, it fails vertical line test. Okay. Second example, f of x equals the square root of x plus 3. Again, if we visualize this graph, it's a square root function. Okay. It's been shifted left 3, so it's really over here. So it is a function. Let's solve for our inverse here. So we're going to switch our x and y. So x equals the square root of y plus 3. To get y by itself, we're going to square both sides. So x squared now equals y plus 3. And then we can subtract our 3 over. Okay. Now, remember that our initial graph, the green one, had a domain of x being greater than or equal to negative 3. Right? That's the smallest we can get before we end up with negative values under that square root symbol. And our range, our y values, started here at 0 and went up. When we do our inverse, that domain and range flip-flop. So now my domain for my inverse is x greater than or equal to 0, and my range would be y greater than or equal to negative 3. Okay? So when we graph this, instead of a whole parabola shifted down 3, we really are just getting the right side of that. Values for x that are 0 or higher, and values for y that are negative 3 and higher. So my inverse, x squared minus 3, it is a function. So I can say f inverse of x equals x squared minus 3. And our reason, again, is it passes a vertical line test. All right. So our last review here is just, again, on those graphs. We're analyzing the transformations. We want to graph the parent function and the transformed function. Try to make our graphs a little darker here. Okay. We want to find the domain and range of the transformed function. So our strategy, describe the shift, make a table of values for the equation up to the x, and then shift it. Okay, so let's think about our parent function. Our parent is just y equals the square root of x. So let's pick some values that we can square root, like 0, 1, 4, and 9. When we square root them, we get 0, 1, 2, and 3. And let's look at our transformations. That negative in front is causing us to reflect over the x-axis. The 2 is causing us to have a vertical stretch. So we're reflecting over the x-axis. We then do a vertical stretch of 2. And then we are going to shift it left 1 and down 4. Okay, so to figure out the best graph, it's easy to move left and down. Let's get our reflection and our vertical stretch taken care of. So let's make a second column here, a second y column, and let's look at what is y when we have it be negative 2 square root of x. So we're going to take all our y values from this, and we're going to multiply them by that negative 2. 0 times negative 2 is still 0. Negative 2 times this 1 would give us negative 2. Negative 2 times 2 is negative 4. And negative 2 times this 3 gets us a negative 6. Okay, so let's plot those points. Again, my blue ones were here, 0, 0, 1, 1, 4, 2, and 9, 3. But we're going to reflect and stretch this. So my green points would be 0, 0, 1, negative 2. Okay, so we reflected it and stretched it. 4, negative 4. And 9, negative 6. Okay, and then our last step is to go ahead and shift left 1 and down 4. So we're going to take each of our green dots and move left 1 and down 4. That's my new end point. Left 1 down 4. Left 1 down 4. And left 1 down 4. So my final graph is going to look like this. Remember, with square roots, we have that end point. It doesn't go past that. My domain for this red graph now, picture the coordinates of this point right here, your end point. We're at negative 1, negative 4. So my x values are starting at negative 1 and moving off to the right. So x would be greater than or equal to negative 1. My y values are starting here at negative 4, but going lower than that. So y has to be less than or equal to negative 4. All right, that's a typical square root graph. Looking at our cube root graphs, again, we're thinking of just the parent function, cube root of x. So we pick some values that we can cube root, like negative 8, negative 1, 0, 1, and 8. The cube root of negative 8 is negative 2. Cube root of negative 1 is negative 1. Cube root of 0 is 0. Cube root of 1 is 1. And cube root of 8 is 2. So let's graph that parent function. Negative 8, negative 2, negative 1, negative 1, 0, 0, 1, 1, and 8, 2. Okay? Then we look at our transformation. We are going right 4 and then up 2. Okay, so we're going to take those dots, move them to the right 4 and up 2. Right 4, up 2, right 4, up 2, right 4, up 2, and right 4, up 2. It's about there. So we have this kind of a twist happening. Remember, for cube root graphs, our domain and range is always all reals. There's no cutoffs to those. All right. It says to rewrite the function to make it easy to graph using transformations. Our strategy is to factor out our perfect number to get a single x. So in that transformation format, we either have that with the index being 2 or the index could be a 3. But notice that we just have a single x when we identify our transformations. In the examples we have here, we have a number in front. So we're going to factor that away from the x. It is still inside the square root symbol. If we factor 25 out of this, we end up with x minus 3. And now that 25 is a perfect square, so I can square root it. Think of square rooting 25 and square rooting x minus 3 separately. The 25 square roots to become a 5. We still have the x minus 3 inside. And then we still have the plus 2 on the far end. Okay, so if we were going to graph that, we could say, I can see the transformations. We have a vertical stretch of 5. We're shifting it right 3 and up 2. Okay, for our cube, we want to try to factor out a perfect cube. 27 can be factored out. We are left with an x and a negative 2. The cube root of 27 is going to come out as a plain 3, and we still have the cube root of x minus 2 and the minus 7 on the end. So again, our transformations, we are doing a vertical stretch of 3. We are shifting it right 2 and down 7. All right, that is a quick overview, or maybe not so quick, but an overview of all the topics in the 6.4 to 6.8 test.